So today we shall discuss differential equations. So first of all, we shall define our differential equations. Now differential equations that are normally the equations and that involves the derivatives. Now suppose we are having the functions, suppose y is a function of x. Now simple derivative of this function that we get dy by dx, or it can be written as f prime of x. Okay, now it is a simple form of differential equations because here it involves the derivative. So in simple form differential equations that can be written in that form, and this is called the first order differential equations. If we have a higher order derivatives like d square y by dx square or d cube y by dx cube, then this is your second order differential equation, this is your third order differential equations. So in simple words, when we are having the derivative, suppose here the dependent variable y, that is a function of x, and if we have the derivative of that functions and the equations that involves the derivatives or that establishes some relationships between the variables and their derivatives, then that equations is called the differential equations. Now the differential equations, it may have different types: first order differential equations, second order differential equations. So we shall discuss first here the first order differential equations. So the first order differential equation it is also called the linear functions, linear differential equations, that also we call the linear differential equation, first order linear differential equation. So in case of first order linear differential equations, when the derivative dy by dx and the dependent variable y, it appear in the first order, and the no product of the form means our dependent variable is not multiplied with its derivative, so it is called in no product of the form y into dy by dx appears, then the equations will be called the first order linear differential equations. So in first order linear differential equations, that takes the general form as dy by dx plus a function u of x into y is equal to another function v of x. So here, like our y, here y is a function of x, u is also a function of x, and v, that is also the function of x. So here this form of equation is called the first order linear differential equations. So in a differential equations, when the derivative dy by dx and the dependent variable y appear in the first order, so here we are having the equation in first order, as the y is not, or dy is not having any power except 1, and no product of the form dy into dy by dx appears, then the equations will be called the first order linear differential equations. And the general form of the first order linear differential equation that can be written as in that way. Okay. Now again, the first order linear differential equations that can be separated in that way, that is first order linear differential equation, differential equation with constant coefficient, and constant term. Okay. Now the first order linear differential equation with constant coefficient and constant term. So here it is the general form of first order linear differential equations. Now we are getting the specific form of first order linear differential equations. Once we will take the coefficient is constant and the term that the function appears on the right hand side, that is also a constant, and in second term we shall consider the first order linear differential equations with variable coefficient and variable term. So today we shall discuss first order linear differential equation with constant coefficients and constant term. What is the specific form of that functions and how do we get the solutions of that first order linear differential equations. Okay. Now when we are telling that the first order linear differential equation with constant coefficients, now your u of x that become a constant, and the constant term then v of x again become a constant. So we can rewrite the equations as, so let that equation be 1. Now the equation 1 that can be rewritten as dy by dx plus ay is equal to b. Earlier in general functions what we did get, that is the coefficient of y, that is a functional form u of x, and the term that is also a functional form, that is v of x. Now the coefficient that is represented by a constant term that is called constant coefficient, because it is the coefficient of y, and the right hand side instead of writing v of x, now we are writing a constant, so it become a constant term. So this is the first order linear differential equations with constant coefficients and constant term. Now if we are getting this function in that way, that is dy by dx plus ay is equal to 0, then it is a first order linear differential equations of homogeneous type. Homogeneous type. And if we write dy by dx plus ay is equal to any constant other than 0 value like b, then it is a case of non-homogeneous type. Non-homogeneous type. So here we have seen the first we have a general concept of differential equations, then the order of differential equations, then we get the first order linear differential equations, what are the general form of first order linear differential equations, then we shall now we are discussing the first order linear differential equation with constant coefficients and constant term. Now if your term, that is that v that become a non-zero value, then it is a non-homogeneous case, and if b is equal to 0, then it is a homogeneous case. So there are different ways how to solve the homogeneous case and non-homogeneous case. So we shall discuss first the homogeneous case, how to solve the linear differential equation, first order linear differential equations of homogeneous case, then we shall discuss the non-homogeneous case. So in case of first order linear differential equations of homogeneous case, let Now the solution solution for homogeneous case. Solution for homogeneous case. So first we are taking our homogeneous case equation as dy by dx plus ay is equal to that b is equal to 0. So it is a homogeneous case. Now if we rearrange the equations, then dy by dx is equal to, we can write as minus ay, is not it? Again, if we take the y on left hand side, then we will be having 1 by y dy by dx is equal to minus a. Now taking the integrations on both sides, if we take the integrations on both sides, then we can write, so taking integration on both sides, we get integration 1 by y, it will be integrated with respect to y, and our dx, it can be shifted in that way. Okay, so taking the integrations of these equations, we are getting in that form. Now integration of 1 by y, that result we know, it is log y. From integration rule we can get that value, and integration of a constant, that we know, we will be getting x. So we are getting ax and plus a constant, that is c. So it is from a simple integration rule we get that value. Now we are having log y is equal to this value. Now if we take the antilog, then we will be getting that log function that can be transformed into exponential function. So here we are having log of y is equal to this value. Now if we remove that log of y, then the right hand side equations, now it will take the exponential function, simply e to the power minus ax plus c. Okay, so ultimately we are getting y is equal to e to the power minus ax plus c, or we can write y is equal to e to the power minus ax into e to the power c, or we can write y is equal to a into e to the power minus ax, where we can write a is equal to e to the power c. So e is an exponential function that takes a constant value, and c is also a constant, so e to the power c, that also become a constant. So a is equal to e to the power c. Now the final equation that we get, y is equal to a into e to the power minus ax. Now to estimate the value of a, we are taking that initial conditions, that if we put x is equal to 0, then what will be the value of y? Okay, now for x, when we are putting the value of x 0, then we can write, then y will be is equal to any constant value that is denoted by y naught. Okay, so when we will be taking our numerical example, then y naught value, that may take any constant value like 5, 6, 10, 20. So for notation, here we have written y is equal to y naught when we are putting x is equal to 0. So when x is equal to 0, putting x is equal to 0, y, then we are getting y is equal to a particular value y naught. Then again turning to our original equation, y is equal to a into e to the power minus ax. Now putting x is equal to 0, we shall get y is equal to y naught a into e to the power a. Now instead of writing x, now the x takes the value 0, so it will take minus a 0. Okay, so ultimately we are getting y naught is equal to a, because here e to the power minus a, that value become into 0, that value become 1. So for definite solution, ultimately we will be getting the definite solution. Therefore definite solution will be getting as y is equal to, now we can write y is equal to a is equal to y naught, that value. So instead of writing a, we can write now y naught e to the power ax. So this is the general solution for first order linear differential equation in homogeneous case. Okay, now taking one numerical example, we can explain further the first order linear differential equations. Now let us take an example. Let us take an example for homogeneous case. For homogeneous case, so we are writing dy by dx plus twice x is equal to 0. It will be twice y is equal to 0. Okay, so on the right hand side, that term becomes 0. Now here the b becomes 0, so it is a homogeneous case. So how can we get the solutions for that? So in homogeneous case, we can get only complementary solution. So in homogeneous case, y of x solution, that is y of x, that can be solved with a into e to the power minus ax. Okay, now here a is equal to 2, because this is our coefficient, constant coefficients, and here the value of a is equal to 2. So we can write y of x is equal to a into e to the power minus twice x. Okay, now putting the conditions here, our conditions here, it is given earlier, it is given that initial condition is that when x is equal to 0, then y of 0 is equal to 5. Okay, so if we put x is equal to 0, then y of 0 is equal to 5, that condition is given. Now we can write for x is equal to 0, so y of 0 is equal to, that value we get here, it is 5. So y of 0 is equal to a to the power minus 2 into 0. Okay, that means 5 is equal to, because y of naught or y of 0 is equal to 5 into a. From earlier equations we get, that is minus e to the power minus 2 into 0, that value is equal to 1. So we will be having only a here. Therefore general solution we get, now we can get the value of a is equal to 5. So 5 into e to the power minus twice x. So this is the solutions for homogeneous case. 5 into e to the power minus twice x. So this is the solution for homogeneous case. Now we shall discuss the non-homogeneous case. So in non-homogeneous case we are having two solutions. One is your complementary solutions and another one is your particular solutions. So let us have a non-homogeneous case. So the non-homogeneous case, first we are taking a non-homogeneous case. So non-homogeneous case that can be written as, so it is a non-homogeneous case. Non-homogeneous case of first order linear differential equation that can be written as dy by dx plus ay is equal to b. Now here b is non-zero value. So as b becomes a non-zero value, so it is a non-homogeneous case. Okay. Now that solution of non-homogeneous case that involves, number one, that complementary solution, and number two, that particular solution, and the general solution that we will be getting after summing up the complementary solution plus particular solution. So first let us have the complementary solutions. So in case of non-homogeneous case, complementary solution, in that case we take, it is a complementary solution that involves a homogeneous part of the given differential equation. So let us convert our non-homogeneous case into homogeneous case. So in particular complementary solution, first we rewrite these equations in homogeneous form. So dy by dx plus ay is equal to 0. Okay, now the solution for this, that is complementary solution that we have derived earlier, the simple solution a into e to the power minus ax. Okay, now the particular solution. In case of particular solution, let us assume that y is a constant value. So in particular solution we assume y is equal to a constant. So if we take y as a constant, then dy by dx, that value becomes 0. So dy by dx plus ay is equal to b. So if we take y as a constant, so with respect to variable, that differentiation becomes 0. So simply from here we are getting that this derivative is 0 because y is a constant. Then we are getting only ay is equal to b. So here y is equal to b by a. So the particular solution that can be written as yp is equal to b by a. Okay. Now the general solution that, therefore the general solution is equal to general solution that denoted as y, that is equal to complementary solution plus particular solution. So complementary solution that we already estimated, that is a into e to the power minus ax, and particular solution that we derived, that is b by a. Okay. Now putting the initial conditions, we can get the value of a. Now putting the value, that is initial condition is that y is equal to when x is equal to 0, then y is equal to, suppose, y naught. Okay, now this is your initial condition. When x is equal to 0, y is equal to y naught. That is our initial condition. Therefore, putting x is equal to 0, we can get y naught is equal to a into e to the power minus a into 0 plus b by a, or we can write y naught is equal to a plus b by a. Therefore, a is equal to y naught minus b by a. So here a is equal to y naught minus b by a. So the final solution that we derive, therefore the final solution or general solution, final solution, that would be y is equal to, instead of a we can write y naught minus b by a into e to the power minus ax plus b by a. Okay, so this is the solution for a non-homogeneous case. Now let us take an example of non-homogeneous case. So non-homogeneous case, the example that we may take, that is dy by dx plus 10y is equal to 20. Now given the initial condition that when x is equal to 0, then y is equal to 5. So the solution that involves, one is your complementary solution and one is your particular solution. Then by summing up the complementary and particular solution, we will be getting our general final solution. So let us have first complementary solution. Complementary solution. So for complementary solution, we convert that non-homogeneous case into homogeneous case. So here we are taking dy by dx plus 10y is equal to 0. Then it becomes a homogeneous case. So complementary solution, yc is equal to a into, here our coefficient become 10, so 10x. Okay, and particular solution, there we may take y is equal to constant. So when y become constant, then we are getting y is dy by dx plus 10y is equal to 20. So as we are taking y as constant value, so that derivative becomes 0. So we are getting only 10y is equal to 20. Therefore complementary particular solution is equal to b by a. So here b is 20 and a is 10, so we are getting that value is equal to 2. Therefore complete solution that involves yc plus yp is equal to a into e to the power minus 10x plus 2. So this is our complementary solution and this is particular solution. Now putting the initial value x is equal to 0, then y of 0 is equal to 5. That value is already given, that initial condition is given. Therefore y of 0 is equal to, we can write a into e to the power minus 10 into 0 plus 2. Therefore y of 0 is equal to a plus 2, or now we know y of 0, that value is already given, that is 5. So 5 is equal to a plus 2. Then we get a is equal to 5 minus 2 is equal to 3. Therefore complete solution y is equal to, now we are getting the value of a, that value of a is 3. So 3 into e to the power minus 10x plus 2. So this is our complete solution for non-homogeneous case. So today we discussed first what is differential equation, then the first order linear differential equation, its form, then first order linear differential equation with constant coefficients and constant term. Again, in case of constant coefficient and constant term, we are having two different cases. One is homogeneous cases, one is non-homogeneous cases. So in case of homogeneous cases, we need only complementary solutions, but in case of non-homogeneous case, we require both complementary and particular solutions, and after summing up the